something that I found fascinating about your paper, about your BDH paper, is you were able to concatenate, literally just like a concatenate operation. You could have one neural network trained on one language, let's say English, and you could have another language trained on, let's say, French, in honor of the macaron here. And with your architecture, and this seems like a rare thing to be able to do with an architecture that could be the building block of a large language model, you can just concatenate those English and French language models together. And because of the sparse activation, it just works, and it's a multilingual model.
That's the spirit, and I think this touches on so many different aspects, which I think are good to highlight, because it's something new. It's new in many senses. As I mentioned before, the transformer, while obviously being an amazing breakthrough in the progress of machine learning and AI in general, does have its limitations in the way we understand its scaling. So if you have like two transformers and you put them side by side, there's no really clear way how to connect them. In BDH, this is much easier in the sense that the model scales in one dimension. We call it the number of neurons, n, and it's like the size of a brain. And then if you want to put two such brains together, you can do it. Depending on what you do, it will be a little bit like a mix of the skills that you had, or you can also do some post-training for the combined brain and make sure it coordinates properly. But definitely, if you just put the brains side by side, you have a model which out of the box has understanding for the different languages, is able to map them into concepts in English, for example, and to work with them.
That is very cool. All right, so with all of these incredible novel capabilities of BDH relative to transformer, so the positive sparse activation that we've talked about, this ability to concatenate that comes out of that, the energy efficiency that comes out of it, and compute efficiency that comes out of it. Where are you today? It kind of sounds like you've, with this paper, with BDH, with the Baby Dragon hatchling paper, we're talking about a billion parameter model, which is about the size of GPT-2 from OpenAI, which is now some years old. And it performs comparably to GPT-2, despite requiring far less compute.
So just to reassure the readers at this point, listeners at this point, we are looking at models which, at a given scale, are on par with models of a given scale. So really, it's given all the progress that has happened in the state of the art, we use that progress obviously. So the 1B models that we produce are comparable or outperform the 1B models out there. The kind of focus, and the reason why we focus on this 1B scale for demonstrations is that this is a scale at which we are able to achieve instruction following and to start testing other capabilities of a model which is able to actually follow instructions and to have the basic capabilities that we would expect of a language model. And this is really for the ease and speed of experimentation. There's nothing particularly stopping us from releasing a super large model like in the 70, 80 billion scale larger. The kind of question which is super pertinent is why do it? Because if you are in the world of language models, just language models, there's a certain market which we could call a bit of a commodity market for the kind of chatbot like applications, discussions, and so on. So
right. So your Claude, your Gemini, your ChatGPT, they're competing in the same space.
I think the switch that most of us are kind of most aware of is if you are working with a reasoning model or not. Usually you are kind of explicitly aware of the switch, especially with models like GPT versus O103, with Claude, etc. You have this option to go into reasoning mode. And this is the place where we don't want to just yet launch a non-reasoning model which is like super large, because there's actually it's not our objective here. What we are doing is we are entering reasoning models. We're entering it from the moderate scale, obviously, but this is a scale where we can display the advantage of this architecture.
I see. I see.
Notably, yeah.
So the most promising avenue for you for moving forward with this baby dragon family is into reasoning models. So models where you don't just have tokens output being spit out to your screen immediately, but there's multiple phases of reasoning happening in the background, refining your answer, ensuring accuracy. Yeah, that's where you see the most potential.
That's it. Lots of consideration, lots of introspection, and also something that we see as extremely pertinent is the ability of reasoning models to work with contextualized inputs and to process them. So if you think of breaking the barriers, the limits of like 1 million token context, but you have a reasoning model which goes through billions of tokens of context. Here you're in a space in which you can, for example, ingest a contextualized data set, private to enterprise, like, a documentation of an entire technology, which is like 1 million pages of paper, 1 million sheets of paper. That's 1 billion tokens. You ingest it in a matter of minutes, given enough hardware on this architecture. And with that in hand, you can start actually making sense of large data sets in the way you would expect of reasoning models. Again, for maybe for the developer audience out there, I'm sure you're familiar with the use case of AI-assisted coding in general. And this is perhaps currently the frontier use case. We're looking at the next generation of use cases like this. But to focus on this use case for a moment, the complexity of having an AI code assistant increases with the amount of pre-existing code, with the size of the code base. And usually it's much easier to have a model which contributes a piece of new code or just invents things without actually having internalized everything that was created before its action. So it's basically doing a project on the side of its own, than to have basically a model which is able to control and contextually operate in an environment which requires understanding of a large code base. And again, code bases are perhaps the frontier example, but they're still the easiest kind of example that we're looking towards.